Dr. Neelu Dhi from Acharya Narendra Dev College, Associate Professor, Chemistry Department. I will be continuing my lecture on conductance today. We were doing Hittorf's rule, according to which loss in cation equivalents at anode divided by loss in anion equivalents at cathode is equal to V plus by V minus, which is equal to T plus by T minus. That is the ratio of the transport number of the cation and the anion. If we add 1 to both sides and invert, we will get loss in the anion equivalents at cathode over total current passed is equal to the transport number of the anion. And similarly, we can get loss in cation equivalents at anode divided by total current passed is equal to the transport number of the cations, that is T plus. Till now, we have not taken the inert electrodes. We have taken the inert electrodes which do not react with the discharged ions. Also, preferential reduction of hydrogen ions at cathode has not been considered. In many cases, anode gets oxidized and hydrogen ions get discharged. In such cases, the concentration around the electrode shows an increase instead of the fall. Electrolysis of silver nitrate solution using silver electrodes is an example of such a case. On electrolysis, the concentration of the electrolyte around the anode increases. There is an increase in spite of the decrease in the concentration due to the migration of silver ions away from this compartment. If no migration of silver ions had taken place from around the anode, the increase would have been higher. This can be determined by placing a silver coulometer in series in the circuit, which measures the total current passed or increase around the anode if no migration of silver ions had taken place, which is the expected increase and is equivalent to the silver deposited in the coulometer. The difference between the theoretical increase and the actual increase gives the decrease in the concentration due to migration of silver ions away from this compartment. The Hittorf's rule enables us to calculate transport numbers and so the relative ionic mobilities from the measurements of the fall in the concentration during electrolysis. The method of calculation is, however, different according to whether the electrodes are inert or attacked during electrolysis. The above two examples which we had discussed earlier can be generalized to include any ionic speed ratio, and it can be illustrated by the following example using inert electrodes. If we consider the electrolysis of hydrochloric acid solution, consider the electrolytic cell shown in the figure divided into 3 compartments, namely the cathodic, anodic and the central compartment. The changes that occur in each compartment on passing 1 Faraday of electricity are: A. The changes in the central compartment. The concentration remains unchanged by the passage of current in the central compartment. Changes in the cathodic compartment. Change in the amount of H plus is equal to change due to the electrode reactions plus change due to the migration effect, which is equal to, due to the electrode reaction, 1 equivalent of H plus ions are being removed from the cathodic compartment. So, we have -1, and T plus equivalent of the cations are moving inside the cathodic compartment. So, we get -1 plus T plus equivalents, which is equal to minus T minus equivalent when we use 1 is equal to T plus T minus. Change in the amount of Cl minus is equal to change due to electrode reaction plus change due to migration effect. Change due to electrode reaction will be 0 for chloride ions, and due to migration effect T minus equivalents are being moved out. So, we get this is equal to minus T minus equivalents. Thus, the passage of 1 Faraday of electricity results in the loss of T minus equivalents of HCl. Then we have changes in the anodic compartment. Change in the amount of H plus will be due to the change due to the electrode reaction plus change due to migration effect, which is equal to 0 minus T plus equivalents is equal to minus T plus equivalent. Change in the amount of Cl minus is equal to change due to the electrode reaction plus change due to the migration effect, which is equal to minus 1 plus T minus equivalents, which is equal to minus T plus equivalents. This amounts to the loss of T plus equivalents of HCl. Thus, by measuring the change in the concentration of the electrolyte either in the cathodic or the anodic compartment, we can find out T minus and T plus of the ions. Measurement of transport number by Hittorf's method. The electrolysis must be carried out in a manner so that intermixing of solutions from around the cathode and anode is avoided. This is done by using a suitable apparatus in which the anode and cathode compartments are separated by a middle compartment connected in the circuit. We can see in the figure U tube constitutes the central compartment which is separating the cathodic and anodic compartments and is connected to the circuit. A silver or copper coulometer is connected in series with the experimental solution so that the same quantity of electricity passes through them. The number of equivalents of metal, silver or copper deposited in the coulometer gives the measure of total current. Since the sum of the two transference numbers T plus and T minus is unity, it is not necessary to measure the concentration changes in both anode and cathode compartments. The apparatus consists of a U tube which constitutes the central compartment. The end tubes contain cathode and anode and constitute anodic and cathodic compartments. The three compartments are separated from each other by stopcocks so that the three portions of the solution can be drawn off separately after the experiment has been performed. The weight and concentration of electrolyte in each portion are measured at the end of the experiment. The change in the amount of electrolyte in each compartment can be calculated knowing the original concentration. If the experiment is carried for a long time, diffusion of the electrolyte occurs due to the formation of concentration gradient. On the other hand, if time is too short, concentration changes are small. Thus, the experiment should be of relatively short duration to minimize diffusive mixing. Small currents must be used because if large currents are used, heating effects occur unevenly and produce convection in the solution, and this mixes up the solution again. Analysis of the central compartment solution should show no change in concentration and thus provides a check on the influence of convection and diffusion. Since the change in concentration of solution results in the change of density and hence the volume, the change of concentration must be determined with reference to a definite weight of solvent and not with the known volume of solution before and after electrolysis. Let the cathodic solution of the electrolysis of HCl using platinum electrodes be analyzed, and let a gram of cathodic solution after electrolysis contain b gram of HCl. The weight of water in this solution will be equal to A minus B grams, and thus we can say that A minus B grams of water is associated with B grams of HCl after electrolysis. On the analysis of original solution, that is before electrolysis, let C grams of the solution before electrolysis contain D gram of HCl. The weight of water in this solution is C minus D grams, and thus C minus D grams of water is associated with D grams of HCl before electrolysis. And before electrolysis, had water been A minus B grams, then the weight of HCl in A minus B grams of water will be given by D into A minus B by C minus D. It may be noted here that the amount of electrolyte is calculated in terms of water present in the solution after electrolysis, which is A minus B grams. So, amount of HCl in equivalents before electrolysis, X is equal to D into A minus B by C minus D into 1 by equivalent weight of HCl, gram equivalents of HCl. The amount of HCl in equivalents after electrolysis, Y is equal to B divided by equivalent weight of HCl, and decrease in the amount will be equal to X minus Y. If in the coulometer W grams of silver is deposited, the total current passed will be equal to W divided by equivalent weight of silver, which is equal to Z. T minus, according to Hittorf's rule, is equal to loss in the amount of HCl in cathodic compartment divided by total current passed, which is equal to X minus Y divided by Z. We can consider another example to determine the transport number of silver ions in a silver nitrate solution. Let us consider the analysis of anodic compartment. In the anodic compartment, after electrolysis, similar to the HCl situation, let A grams of the anodic solution contain B grams of silver nitrate. Weight of water in this solution will be equal to A minus B grams, and thus A minus B grams of water is associated with B grams of silver nitrate after electrolysis. Before electrolysis, C gram of the anodic solution contains D grams of silver nitrate. Thus, weight of water in this solution is C minus D grams. C minus D grams of water is associated with D grams of silver nitrate before electrolysis. Thus, before electrolysis, the weight of silver nitrate in weight A minus B grams of water will be given by D into A minus B by C minus D grams. Before electrolysis, the weight of silver nitrate in weight A minus B gram of water is given by D into A minus B by C minus D grams. It may be noted again that the amount of electrolyte is calculated in terms of water present in the solution after electrolysis, which is A minus B grams. Concentration in equivalents before electrolysis, X will be equal to D into A minus B into C minus divided by C minus D into 1 by 170 gram equivalents of silver nitrate. Concentration of in equivalents after electrolysis, Y will be equal to B by 170 gram equivalents of silver nitrate. Now we can have two cases. Case 1, when electrolysis is carried out using platinum electrodes which are not attacked by any of the ions, then Y will be less than X due to migration. Fall in the concentration around anode will be equal to X minus Y. And suppose in the copper coulometer connected in series, the weight of copper deposited in the same time was W grams. Total current passed will be equal to W divided by equivalent weight of copper, which is equal to Z, and thus the transport number of cations, that is silver ions, will be equal to X minus Y divided by Z. Case 2. When electrolysis is carried out by using silver electrodes, the nitrate ions attack silver anode, bringing silver ions into the anodic compartment. According to the equation, silver gives silver ions plus electron. The concentration of the anodic compartment will therefore tend to increase on account of this factor. In such cases, Y will be greater than X. Therefore, increase in concentration round the anode will be equal to Y minus X gram equivalents. Further, we know that gram equivalents of copper deposited on copper coulometer is equal to gram equivalents of silver deposited on the cathode of the electrolytic cell, which is equal to gram equivalents of silver dissolved from anode of the cell by the action of nitrate ions. Since gram equivalents of copper deposited is equal to Z, it follows that increase in the concentration of silver ions Ag plus in the anodic compartment would have been Z gram equivalents, but actual increase is Y minus X gram equivalents. Therefore, Z minus Y minus X. Expected increase is Z, actual increase is Y minus X. So, Z minus Y minus X gives the fall in the concentration of Ag plus in the anodic to cathodic compartment due to migration. T plus Ag plus will be equal to Z minus Y minus X divided by Z. That is, the transport number T plus of Ag plus is equal to the expected increase minus actual increase divided by expected increase. So, this was Hittorf's method. There is another method which can be used to determine the transport number of ions, which is using moving boundary method. In this method, that is the moving boundary method, the motion of ions under the influence of an applied potential is observed directly than through the concentration changes at the electrodes as in the Hittorf's method. We can see the figure of moving boundary method to determine the transport number of ions. The apparatus consists of a long vertical tube of uniform area of cross section A fitted with two electrodes at two ends. Let us consider the electrolyte AX called the principal electrolyte, the transport number of whose cation A plus is to be determined. A layer of this electrolyte is generally introduced above the solution of another suitable electrolyte called the indicator electrolyte, and it is subjected to three conditions, namely, first, the anion X minus should be common to both the electrolytes. Second, the cation B plus should move slower than cation A plus. Third, the electrolyte Bx should be more dense than Ax. The boundary between these two electrolytes is visible because of difference in refractive index of the solutions or in some cases a difference in color. On passing current, passing current between the two electrodes, both the cations A plus and B plus ions move upwards towards the cathode, while the anion X minus moves downwards towards the anode. Thus, the boundary between the two solutions is moved up, which can be followed by the refractive index measurements. Let the boundary move from A dash to B dash, distance being equal to L, after passing Q Faradays of electricity. Then the volume of the liquid moved will be equal to A into L. Concentration of the solution AX is equal to C gram equivalents per liter. Number of equivalents of A plus carried towards the electrode will be equal to LAC by 1000 Faradays. Transport number A plus of the cation will thus be equal to LAC by 1000 divided by Q. Since B plus ions have a lower velocity than A plus ions, they will never overtake the latter, and a sharp boundary is always maintained between the two solutions. For the electrolyte other than univalent electrolyte, the amount of Az plus carried towards the cathode in equivalents will be equal to nu plus LAC by 1000 divided by Q, where nu plus is the stoichiometric coefficient. The corresponding amount of electricity carried will be equal to nu plus Z plus LAC by 1000 divided by Q, and thus this will be equal to the transport number of the cation, that is T plus is equal to nu plus Z plus LAC by 1000 divided by Q. We can have a numerical based on the moving boundary method, which you can practice on your own. The answer is also here. Now we have to discuss abnormal transference numbers. Let us take a break of 2 minutes and then I'll continue from here.